Good morning. My name is Jorge Alberto Gaitangrir, and today I'm going to be presenting the final submission for the design and chemical process problem statement, which is related to the production of ethylene oxide. In this case, this is the following index that will be taken into consideration, which revolves around the aspects of energy integration, equipment design, risk analysis, and conclusions. Here, as it can be seen, it's the energy integration section. The first step that was taken into consideration for this final submission was the possibility of making an energy integration with 7 of the current heat exchangers present on the process, with the goal of reducing the annual usage of utilities, decreasing the annual utility cost. After doing the stream analysis, it was determined that the pinch point, as it's shown in the presentation, it's located at 201 degrees Celsius with a change in temperature of minimum with 10 degrees Celsius. After the pinch point was obtained, the heat exchanger network was designed with the help of the software Aspen Energy Analyzer. And it is important to state that the energy integration has some rules that need to be followed in order to exchange heat. For the energy integration, the rules that were taken into consideration are stated as follows. Above the pinch point, the number of cold streams and the respective heat flow rate should be greater than the hot streams, and which is opposite for below the pinch point, where the number of hot streams and the respective heat flow rate should be greater than the cold stream. As it is shown in the figure provided in the presentation, some divisions needed to be made to achieve the compliance of this rule, because below the pinch point, some cold streams had a higher heat flow rate than the hot streams, and there were more cold streams present as the divisions were made. To conclude with the section of energy integration with the analysis of utility costs by the book used in this course, it was determined that 92% of the cost previously used in utilities is saved by the usage of the new heat exchanger network. However, a more profound economic analysis is needed to determine the impact of the new heat exchanger used in the process, because these heat exchangers are a fixed cost in inversion, whereas the utility cost is something that happens annually. The next section of the analysis in the presentation is the design of the equipment. And the focus will be here in the heat exchangers, particularly the condenser present in the distillation column. In here, there were some assumptions that needed to be made in order to dimension the equipment. For example, that the process stream entering the condenser only experiences a phase change, maintaining the inlet temperature as the target temperature, which is 86.4 degrees Celsius. The second assumption was that the correction factor is equal to 1 due to the previously mentioned phase change that is occurring. The assumption number 3 that was made is that the condenser is operating with the streams flowing counter current. Also, apart from the assumptions that were made, some heuristics needed to be taken into consideration. For example, that the minimum temperature for fluids is 10 degrees Celsius. And also that the cooler water inlet temperature is 30 degrees Celsius with a maximum outlet of 45 degrees Celsius. And at last, that the heat transfer coefficient for condenser is 850 watts per meter squared Kelvin. After making the different calculations based on the assumptions and the heuristics previously mentioned, the results were obtained, which are showed currently in the presentation. All of the equipment, aside from the ones obtained in the energy integration, are shown in this section of the presentation with the respective dimensions and parameters. To conclude, it can be shown the different equipments used and that were dimensioned by the use of heuristics and assumptions. As the last section of this presentation is the risk analysis, which is very important because the process of ethylene oxide can be very dangerous if there are not some measurements taken into consideration. For example, in the upstream, identifying the reactor number 702, there can be shown that upstream could be the risk of less recovery of ethylene oxide, higher temperature feed, and excess pressure. In the reactor itself, there could be some explosion risk, excess of reagent or production combustion, and catalyst fouling during the clogged tubes. And at last, in downstream, there could happen damage to the pipeline equipment, less product purity, and more CO2 produced with the excess production due to the high conversions. In the case of this risk, it is important to consider an action plan to decrease the probability of risks taking place and instructions to de-escalate situations where risks are currently present. To conclude with this section, risk analysis is crucial when developing an industrial plant due to a responsibility that comes with the risk with information at hand. In conclusion, the design of chemical processes involves different aspects that should be taken into consideration for the proper functioning of the plant, which range from the design of the equipment to the risks that can take place in the process. To conclude, the chemical engineers should have and maintain a high moral compass due to the risks that may be present with industrial plant operations and follow the norms and rules that are already established to ensure the safety of those operating in the plant and those surrounding it. Thank you.